So in Chapter 10, we're going to discuss water and solutions. So to start off with, household water is probably the most familiar to us as being important for society because everyone can think of ways in which they are using household water throughout their day. Now, all of our household water is going to originate from streams. These include things like rivers, lakes, groundwater, and rain capture. So streams and lakes are both what we would call surface sources of water because they're above ground, whereas groundwater would be things that's in like an aquifer. Okay, and then rain capture, rain collection, anything like that is going to be a source of household water. Now, when we look at this pie chart is telling us what the average household water usage is being used for specifically. So when we're looking at the pie chart, we're looking at lawn and garden, toilets, and bathing. So almost the entire pie chart minus approximately 19%. So 81% of our water, household water, is used watering our yards, flushing the toilet, and then bathing. So taking showers, things like that. The other 19% is laundry, cleaning dishes, drinking, and cooking. And so we use an alarming amount of fresh water in our households for things that are not considered to be essential or required for life, but they are important, they are part of our society. So when we have water conservation, if you've ever grown up in a city where they do conservation and they start restricting how you can use your water, especially in summer when there's been a drought, the first thing they usually do is say, well, you can only water your lawn and garden on the days. If your zip code ends in a 0 or a 7, you can water on Mondays and only Mondays. And then if you get caught disobeying it, then they fine you. So properties of water that make it important from a chemistry perspective is one, it's the major constituent of living things. It is the 70% of your human body. It makes up your cells. It's also one of the primary quote unquote ingredients in food. We know that our world is about 72% covered in water. So we know that water is a main player in the game of life because it's everywhere in our world. But there are some things that make it important in other ways. One is that it's called the universal solvent, and it's called that because it dissolves most molecules. Most things we have will dissolve in water to some degree. Some dissolve really easily, and some need a little bit more effort. The next thing is that the solid phase, so ice, is less dense than liquid water, meaning ice floats. This is not foreign to us, but it's really important because if ice was heavier than liquid water, the lakes would freeze from the bottom up, meaning that the fish would have nowhere to go. But because the lakes freeze at the top, the fish get to live underneath the ice layer, and they're actually pretty warm inside that pond of water with the ice on top. So it's essential for life. The next thing is that water has a high specific heat. So you think back to our MCAT equation that we talked about when we did heat and temperature. And what this means is it takes more heat to warm water up. So if I was heating the same amount of soil and water side by side, the soil is going to heat up 5 times faster than the water, which is why on a hot summer day it still feels good to jump in a pool, because the pool water is cold, and that's because of the high specific heat capacity of water. The next one is the high latent heat of vaporization, and really what this means is you can evaporate just a little bit of water and you're going to feel very cool. So for us, evaporative cooling, and even dogs and cats when they pant, that is essentially how they sweat. And so when you are sweating, you're actually evaporating water off your skin, which is a cooling mechanism, and that works as well as it does because of the high latent heat of vaporization of water. The next thing is that snowflakes always have 6 sides, and each and every single snowflake is going to be 100% unique. So what contributes to that unique structure of snowflakes is the structure of water. The electrons between, remember we think about water, H2O, The electrons that are going to be shared between the oxygen and the hydrogen, remember this represents 2 electrons. Well, these electrons are not evenly shared. If it was a tug of war and oxygen and hydrogen were tugging of war for the electrons are actually going to be located a little bit closer to the oxygen. Okay, so it means that oxygen is going to hold those electrons pretty closely to it, making it kind of negatively charged. Even though it's not negative like an anion, because it's hogging those negative electrons, it's a little bit more negative than the hydrogens, which are going to be a little bit more positive. What this creates is a polar molecule. And what that means is all of those properties that we were talking about before are going to come down to this unique bonding, which is called hydrogen bonding. The hydrogen bonding accounts for these unique properties, and the hydrogen bonding occurs because of this unequal distribution of electrons. There's a strong bond between the hydrogen of one molecule and then the fluorine, nitrogen, or oxygen of another. Let's just say oxygen. So if we look at this here, this is H2O, and we said that this is more negative, this is more positive, negative, positive. So what you can see here is that the negatives and the positives are actually pointing at each other. And that's not a mistake. That is the same type of electrostatic attraction that holds our ionic compounds together. And just like electricity, where we talked about unlike charges attracting. And so the way that these oxygen or water molecules arrange themselves, it may look like a hexagon to you. And it is. It's the same hexagonal shape which produces those beautiful 6-sided snowflake colors, shapes. All right, so let's talk about solutions. Solutions are not the answer to a problem, but solutions are still important to chemistry and biology. So dissolving is going to be the process of making a solution. We're going to dissolve something into something else. When we make a solution, we're going to define this as a homogeneous mixture of ions or molecules from 2 or more substances. So it's important that you realize that sometimes we use the word solution in place of homogeneous mixture, and vice versa, and because they really are referring to the same thing. A solution is a homogeneous mixture, and a homogeneous mixture is a solution. There are 2 components of a solution which are important to us. The first is the word solvent, which we've heard before because we said water is the universal solvent. Now, the solvent in this case is going to be the component of the solution which is present in the majority, in the larger amount. Okay, so we're going to say that it's going to be the majority. The solute, on the other hand, is going to be what's being dissolved in the solvent. And what this usually means is this is going to be the minority component, the one that's found in the least amount. But the solvent is usually going to be the most. So when you make salt water, you take a lot of water and you put a little bit of salt in it, comparatively speaking. Now we have a specific type of solution that's called an aqueous solution. And anytime you see the word aqueous, you should always think water. And the aqueous solution is going to be where the solute is a solid, a liquid, or a gas, but the solvent is always water. Okay, so that's what makes it unique. Any solution can have a solid, liquid, or gas solute, but an aqueous solution is only going to have a water solvent. So 2 more terms used to describe solutions. We're going to have what's called miscible and immiscible fluids. So we're not talking about solids and gases. We're only talking about liquids at this point. Okay, so those are liquids. When 2 liquids are miscible, they are going to mix. We can add them together, shake them up, and they're going to create a homogeneous solution. We can't see one from the other. So an example would be taking carbonated water and orange juice, and we can create a carbonated orange juice beverage, but we can't see anywhere in here where the orange juice is that the carbonation is not. It's very clearly homogeneous. Immiscible, on the other hand, is when 2 or more fluids will not mix. And so you can see here, it's a great example. It almost looks like candy corn, but there are 3 layers of a liquid that are not going to mix together. I could probably shake this container up and eventually they're going to settle back out into their layers. But if I shake hard enough, I could destroy some chemical bonding, some attractive forces, and maybe it's not going to quite go back to the way it was. But this is immiscible. They are separate layers, distinct layers. So solubility. Solubility is going to be how well something dissolves in a solvent. Some things are going to dissolve really well, like salt, sugar, things like that. Your baking soda, but other things are not going to dissolve. Sand, dirt. They don't dissolve in water, and for good reason. We don't want the sand dissolving in the water. We don't want the dirt dissolving in the water. But when we're talking about in chemistry, there's going to be a limit of solubility. We have a range. Some things are going to dissolve really readily, and other things are not at all. But we're also going to have what's called unsaturated, saturated, and supersaturated. And the way to tell them apart is just as this image below shows us. Unsaturated is where I can continue to add the solute to the solution, to the solvent. So I can continue to add the salt. I can continue to add the sugar, and it's going to dissolve. Once I get to a saturated solution, the solute will no longer dissolve. At this point, we're going to start to see the salt or the sugar settle out at the bottom. And no matter how much I mix, no matter how much I stir, it's not going to dissolve. Now, supersaturated is going to be a really unique thing that happens, is that when we add so much that eventually crystals start to form. And this is supersaturated. Now, the next thing is to talk about insoluble substances. And these are things that are not going to dissolve. And we talked about some examples. Sand, dirt. These are insoluble. No matter what we put them in, they're probably not going to dissolve easily. Now, there is a simple rule that helps us determine when things will mix or when they will dissolve. And the simple rule is that like dissolves like. Things that are polar, like water and salt, water and sugar, are going to dissolve quite well together. Non-polar substances will also mix together. But when we try to take a polar and a non-polar substance and put them together, they're not going to dissolve. And so that's what we see here. This is oil and water. Water is polar. Oil is non-polar. They are not going to mix. So other things that are an example are gas. Gas is made up of non-polar substances and it does not mix with water. But if I took oil and gas and mixed them together, they would mix. So we're going to take a break here and give you a minute to stretch your legs and then come back and finish up part 2 of chapter 10.